Hey everyone, Mr. Fransky here. I'm going to apologize in advance. I'm in the San Francisco airport with a very high-powered microphone. So anything that you hear on the outside, I apologize, and hopefully you're able to hear me clearly enough. So today we're going to talk about 8.3. This is growth rates of functions, and we're going to use L'Hopital's rule. Remember, L'Hopital is kind of what we've been talking about so far. We're going to use L'Hopital's rule to be able to compare the growth rates of different functions. So let's jump in and take a look. First thing I want to do is just do a few Bellward problems with L'Hopital's rule, a few of the different indeterminate forms. Remember those indeterminate forms, 0 over 0 is one of them, infinity over infinity, right? Those are the easy ones. Some of the other ones we had were 1 to the infinity. I got to remember these. I think infinity to the 0 is one of them, right? 0 to the infinity. These are some of the ones that we saw that were going to be difficult problems. Sorry, 0 to the infinity is not one. So anyway, let's jump in and try some of these and see what we find. So the first one, if we take a look at this, we have 3x cubed minus 4x squared plus 1 over 2x cubed. We plug in infinity, we get infinity on the top and infinity on the bottom. Now remember with this one, we really learned a way to do this before, right? The degrees are the same, so we should just be able to do 3 halves, but just for fun, let's do L'Hopital's rule and see if we get the same thing. So if we take the derivative of this guy, our little notation, so we'd have 9x squared minus 8x over, there's 6x squared. Still infinity over infinity, so we can use L'Hopital's rule again. So we're going to have 18x minus 8 over 12x. L'Hopital's rule one more time. So we'll have infinity over infinity, going to be 18 over 12, which does indeed reduce if we divide both by, 6, reduces to 3 halves. Awesome. Okay, so it works the way we think it should. Next one, if we go to infinity, this is an infinity times tangent of 1 over infinity. That's tangent of 0. So we have infinity times tangent of 0, which is infinity times 0. That is indeed one of our indeterminate forms. This is one, remember, we have to churn into infinity over infinity or 0 over 0. So I'm going to rewrite this. I'm not using the rule yet, so I'm not putting an L there. X approaches infinity of tan 1 over x divided by 1 over x. Because if I think about it, now, if you plug in infinity, on the top you have tangent of 0, which is 0, and on the bottom you have 1 over infinity, which is also 0. So this is a 0 over 0, so we can now just use straight up L'Hopital's rule. So this is going to be, I should have carried my limits up here, but I didn't. It's a little bit of shorthand, it's okay if you don't. So we take the derivative of the top, we have secant squared of 1 over x times the derivative of 1 over x, which is negative 1 over x squared. On the bottom, derivative of 1 over x, we just did that, it's negative 1 over x squared again. Remember, that's just the power rule, right? X to the negative 1 to the front, reduced to a negative 2. So now those cancel. That's nice. Now if we plug in infinity, we have secant squared of 0. Secant of 0 is 1, so 1 squared is 1. Someone always asks me, it seems like we always get 1 on a lot of these. That's true. There are a lot of answers to these that turn into 1, a lot of them turn into 0, and a lot of them turn into infinity or undefined. Let's take a look at the next one. So where x is going to infinity, we have natural log of infinity minus natural log of infinity. Natural log of infinity, remember, natural log grows really slowly. We're going to talk more about that today. But it does eventually go off to infinity, right? It grows very slowly, but goes to infinity. So this is an infinity minus infinity. So remember, when we have that, we have to somehow combine the two. Now there's no common denominator I could find. But what I could do is I could combine these using log rules, right? Subtraction turns to division within the log. So the limit is x approaches infinity. I haven't used L'Hopital's rule yet. I haven't done any derivatives. So I'm just going to do this as 2x over x plus 1. Now, if you think about plugging in infinity here, we have infinity over infinity inside that log. One of the limit rules is that you can pull that limit inside. But I think I can just think about this for a second, right? We have the same degree on the top and bottom. So this is the limit as x approaches infinity of natural log of 2. Right? As x goes to infinity, it just turns into natural log of 2 because it's 2x over x. So that is just natural log of 2. I've taken away all of the x's, and we have our final answer. That's it. I always like these ones because you're subtracting 2 infinities, and the difference is always getting closer and closer to natural log of 2. I think that's kind of cool. This next one, if you couldn't see, it's an exponent. So x is approaching 1. So this is 1 to what power? Let's see. 1 over 0, that's 1 to the infinity. That is indeed one of them. That's the one that's like the potential energy one, right? You either go a little to the right and it becomes infinity, or you go a little to the left and it turns into 0, right? So it could be either way. We're not sure which way it's going to be pulled, or it could turn into some weird number. So remember, with these exponent problems, we're going to have to use logarithms, right? So I'm going to use natural log. So I'm going to do, this is the same as the limit of x approaches 1 of the natural log of x to the, e to the natural log, x to the 1 over x minus 1. And we're going to kind of ignore the e for a second. We'll come back to that later, right? So just remember to do the exponent at the end. So we're going to focus just on the natural log part, okay? So I'm going to do 1 over x minus 1 times the natural log of x. Now if we plug in 1, natural log of 1 is 0. So we have 0 times infinity. So what I'm going to do is I'm going to rewrite this. I got to think about how I'm going to do this. I think here. So we have, this is our infinity, this is our 0. So what I'm going to do is I'm going to change this to, put it on top, we'll have 0 over 0, sorry, ln of x divided by x minus 1. Right, we just slid it up on top. So now we have 0 over 0, now we can use L'Hopital's rule. So use L'Hopital's rule here. Derivative of ln of x is 1 over x. On the bottom we have just 1. This is just 1 over x. As x approaches 1, that is 1. Is 1 our answer though? No, because of this whole natural log thing, we got to do e to the first power, which is... Alright, so hopefully this L'Hopital's rule stuff is becoming easier. Today we're going to do some stuff with L'Hopital's rule to talk about comparing growth rates of functions, which isn't too bad. So first of all, let's just kind of think about what a growth of a function means. I've used this this kind of talk, or this kind of vocabulary all year. Is a function grows faster. Right? So we talked about a function, one function grows faster than another. And the first place that we talked about it was where we had like limit as x approaches infinity. So we're looking at horizontal asymptotes of like, I don't know, x cubed over 2x squared minus 1, something like that. We said, well, we have the cube on top. That function is going to grow faster than the bottom. And so this is going to end up being infinity, right? It's not going to approach any number because the top is growing so much faster. We used to say it wins, right? The top is going to win, which means that the bottom loses, and it's going to end up going off to infinity, right? So, we're going to kind of formalize this today. Talk about how to actually prove if a function grows faster or slower or at the same rate as another one. So, some of the functions that we know that grow to infinity. Linear functions like f of x equals 2x plus 1, right? That function just linearly grows to infinity or something like that, right? We can have higher degree polynomials, right? Like 3x cubed minus 2x squared plus 5x minus 1, right? The cubic function would look something like this. And I think we all would agree that this would grow faster than a linear, right? Linear has a constant growth rate. This would be growing faster. As x increases, this is growing faster. Then we get to the more interesting ones, like e to the x. Right? E to the x grows pretty fast, right? Exponential functions we know grow very, very quickly. As x gets bigger, you're multiplying by that e more and more times, as opposed to this one where you're just multiplying by itself more and more times, right? And then we have functions like natural log x, right? Natural log x definitely grows to infinity, but it's growing concave down, so it's growing slowly, right? So how can we actually compare these things? Let's come up with a kind of a formal way to talk about this. So if you're given two functions, f of x and g of x, and I want to know which one grows faster. So usually there are two kinds of questions you get with this. You get, show f of x grows faster than, slower than, or at the same rate as some other function g of x. So we have to have a way to be able to prove that or show it. And sometimes you're also just asked, how does the growth rate of f of x compare to g of x? So given one function, how does it compare to the other one? So you could choose to make it grow faster, slower, the same. You need to figure that out. So in general, what you do for this, you take a limit as x goes to infinity, because we're asking as x gets very big, which one's growing faster. You compare f of x to g of x like this, f of x over g of x. So you take the two functions, just divide them by each other. Now you can probably already figure out where this is going. If this limit ends up being infinity, which one grows faster? F of x grows faster, right? Because, I'm going to lowercase there, because if f of x over g of x, as x goes to infinity, if f of x wins, if it's big enough to push this all the way to infinity, that must mean f of x grows faster. If it ends up being a number, like 5, or e, or 1, right? So a number that is not 0, then they grow at the same rate. Same rate. Okay? So an example for that would be like 3x squared over 5x squared, right? The x squareds cancel. These, even though the 5x squared seems like it's tempting, it's going to grow faster, this rate is, this difference kind of, you can think of between the functions, or the quotient of the functions, is 3/5 all the time. That rate of f of x is never going to take off faster than g of x. They're going to grow at the same rate. As x increases, they both kind of increase the same amount. Then the last option is, if it's 0, if this limit equals 0, that means that g of x grows faster, or usually we say f of x is slower. So in general, you kind of want to look at the top function as the one that you want to compare. So is f of x faster than g of x? Is it slower than g of x? Or is it growing at the same rate? Now you could argue at the same rate thing about like it being a number, like wait, it doesn't seem like that really makes sense, that one's growing slower or faster or the same. But that's just how they choose to define two functions growing at the same rate if you get a constant number that is not 0. So let's try some. So show that e to the x grows faster than x squared. So this is something we should know, right? But the thing we're going to do here is we're going to take the limit as x approaches infinity, e to the x on top, x squared on the bottom, and we're going to show that this ends up being infinity. If we can show that this goes to infinity, that's going to prove e to the x goes faster than x squared. So this gives us infinity over infinity, so what do we use? L'Hopital. So we have e to the x still on the top, on the bottom we have 2x, still infinity over infinity, got a L'Hopital again, so we have e to the x over 2. Now as x goes to infinity, the top is infinity, the bottom is just 2, that is infinity. So this shows, therefore, right, 3 dots means therefore, if we've done proofs before, e to the x is faster than x squared. Okay, so a little proof to show that e to the x goes faster than x squared, not too bad. Alright, next up. How does the growth rate of natural log of x compare with x? How about x squared or root x? Okay, so we're going to try ln x. We know ln x goes very slowly, right? It's a concave down function. And when we think about x, x is linear, so I'm guessing that's going to grow faster. X squared is concave up, so I'm pretty sure that's going to grow faster. But root x is kind of an interesting one, right? Because root x also grows concave down. And the question is, does it grow slower or faster than natural log? Well, to prove this, we're going to do some limits, right? So this is the limit as x approaches infinity. So we're going to compare natural log. Let's do natural log on top. Divide it by x. Plug in infinity, infinity over infinity, so use L'Hopital. 1 over x divided by 1, that's just 1 over x. As we put infinity in there, it gives us 0 over 1, that is 0. So ln x is slower than x. Okay? Let's try the next one. X approaches infinity, ln x over x squared. Now this one should be even worse, right? Because the bottom we now know is growing faster than the x. So we use L'Hopital, 1 over x divided by 2x. So if we rewrite this, this is 1 over 2x squared. As x goes to infinity, that's going to go to 0 even faster. So ln x is definitely slower than x squared. Good. Now this last one is the kind of interesting one, right? So when we limit as x approaches infinity, ln x over root x. So we use L'Hopital, because infinity over infinity still, as x goes to infinity for both of these, they go slowly, but they go to infinity. So we have 1 over x upstairs. And on the bottom, derivative of root x, you might have to remember this. You probably had it memorized back in chapter 3, but you might have to remember it now. So the 1 half comes to the front, x to the negative 1 half, right? 1 half, x to the negative 1 half. That negative 1 half goes to the bottom. This is 1 over 2 root x. So you multiply by the reciprocal of the bottom. It's not looking good. It looks like natural log might be growing faster when we put this to the top, but watch what happens. 2 root x over x. Root x is x to the 1 half, so this is 2x to the 1 half over x. That is, so 1 half minus 1, if you think about your exponent rules, is 2 over x to the 1 half, or 2 over root x. So even though root x goes slowly, as x goes to infinity, this is still going to 0, so ln x is also slower than root x. Okay. So, ln x is kind of the bottom of the barrel. This is what I've also often heard it called. Is that it's about as slow as you can grow. It does grow to infinity, but so ridiculously slowly, right? And the reason for that is because e to the x grows so fast, right? E to the x grows so fast, that's a terrible e to the x. Sorry, I'm trying to write on my lap here. But e to the x grows so fast is the inverse, and so it's going to grow very, very, very slowly, but it will go to infinity, even though pretty much anything, cube root x, fourth root x, anything is going to grow faster than natural log. Alright, so now let's take a look at one that's just a little bit weirder. In this case, we're going to be looking at x plus sine x, which is compared to x. We think sine x might make it go kind of up and down. We're going to show us these actually grow at the same rate. So what we're going to do is we're going to take our limit as x approaches infinity. Now, what happens is you might try to go down this road. You might try x on the top and x plus sine x on the bottom. What happens is if you start using L'Hopital's rule on this, it actually won't work, which is frustrating. And instead, what we can do is we can try to use some limits that we already know. So what if we flip this over? Because if you do it in one direction, you should be able to do it in the other. Because if we do x plus sine x over x, if it equals a number in this direction, then in the other direction it should work as well, right? And if this ends up equaling infinity, then the opposite direction would equal 0. So we're still going to be able to show if one's faster than the other. What I'm going to do now, I'm not going to use L'Hopital's rule right away. I'm just going to split this into two pieces. This is the limit as x approaches infinity. So butterfly, heart breaking apart, whatever you want to call it. X over x plus sine x over x. So that is the limit as x approaches infinity of 1 plus sine x over x. Now sine x over x is that famous one we've talked about before. You can use L'Hopital on it, right? Cosine over 1. But we know that this is 0, so this is just 1. So that shows that these will grow at the same rates. That's all there is to it. All right. So now a couple head scratchers. So compare the growth rates of 2 to the x and 3 to the x, or e to the x and e to the x minus 2, e to the x and e to the x over 2. So these are ones that kind of take a little bit more thinking. The limits are a little bit harder to compute. Let's give it a shot. So 2 to the x and 3 to the x. I'm going to do it up here. Limit as x approaches infinity. Let's put 2 to the x on top. 2 to the x over 3 to the x. Now what happens is, if you start taking derivatives of these, I know you guys are pros at the derivatives of a to the x now. The top would be 2 to the x times ln of 2, and the bottom would be 3 to the x times ln of 3. Now the problem is, if we keep doing this, you just keep racking up ln2s and keep racking up ln3s. Those are constants, right? So you just have to worry about the derivative of 2 to the x and the 3 to the x. So this doesn't get you anywhere. What you have to do is you have to basically do what we did to first prove those derivatives. So I'm going to rewrite this a little bit. Limit as x approaches infinity. On the top, I'm going to write this as e to the natural log of 2 to the x. On the bottom right is e to the natural log of 3 to the x. Right? These are inverse functions, so I haven't changed anything. Right? E to the natural log of 2 to the x is 2 to the x. E to the natural log of 3 to the x is 3 to the x. Then move those x's to the front. E to the x ln 2. On the bottom we have e to the x ln 3. Now, multiplication here, right? We changed powers to multiplications. Multiplication of powers is the same as power to a power. So I'm going to write these as e to the x to the ln 2 and e to the x to the ln 3. Now we have the same base on the top and the bottom, different exponents. So we can rewrite that as the limit as x approaches infinity of e to the x to the power ln 2 minus ln 3. So that's an exponent of an exponent. Now ln 2 minus ln 3, we use our log rules again on that. The limit as x approaches infinity, e to the x to the power ln 2/3. Right? Because ln 2 minus ln 3, subtraction turns into division inside the log. There we are. Now what I'm going to do is I'm going to change this back to multiplication and put that exponent back on the top. So this is the limit as x approaches infinity, e to the ln of 2/3 to the x power. Now I'm going to use the same thing we used to get this into an exponent form. This is e to the ln of something. Those are just inverses. They cancel each other out, sort of. So this becomes, I'm going to write it over here so I don't run out of space in the next problem. That is just 2/3 to the x power. So limit as x approaches infinity of 2/3 to the x power. Now 2/3 is less than 1. So if you remember your exponential growth, exponential decay from pre-calc, this is going to decay down to 0. So that means that 2 to the x actually grows slower than 3 to the x. Interesting. So I kind of think about this as like x squared and 2x squared. And those actually grow at the same rate, right? This just grows at a rate of 2 faster, so it's a constant between them. This, with exponentials, actually, if you have b greater than a greater than 1, then b to the x grows faster than a to the x. That's kind of a fun little proof to do if you want to try it. So if b is greater than a greater than 1, b to the x will always grow faster than a to the x. It pretty much follows the same proof, but it's kind of interesting to think about. So now these guys, similar idea, but actually easier algebra. So let's try it. So we have e to the x, let's try the first one, let's approach infinity, e to the x over e to the x minus 2. Now, you might be tempted once again to just try taking derivatives right away, but what you'll find is the derivative of e to the x is always e to the x. The derivative of e to the x minus 2 is always e to the x minus 2, because the derivative, if you chain rule this, will always just be 1, right? That's not going to change there at all. Sorry, that was kind of loud. Hope you hear me. So what you're going to do instead is just use your ideas of exponent rules. This is the limit as x approaches infinity. On the top, we have e to the x. On the bottom, e to the x minus 2, that is e to the x times e to the negative 2. Right? We can split that up because they're the same base, so you just add the exponents. It's the same thing. Then the e to the x is canceled, so we have the limit as x approaches infinity of 1 over e to the negative 2. That is just 1 over, that's just e to the second power, right? Negative flips to the top. So the limit as x approaches infinity of e squared. That is a value. That is e squared. So these are the same rates because we got a number, right? We didn't get infinity or 0. We got a number. So e to the x minus 2, same rate. That kind of makes sense because e to the x minus 2 is just this function shifted to the right 2. Same thing. Next one, a little bit different. Let's try it. Limit as x approaches infinity, e to the x over e to the x over 2. So e to the x over 2, we can think about that as a power to a power. So I'm going to write this as limit as x approaches infinity. Lots of exponent rules here. Hopefully you guys were good at that pre-calc. So we have e to the x over e to the x to the 1/2, right? Because e to the x over 2, same with e to the x to the 1/2, because you can multiply those powers, you get e to the x over 2. So that is limit as x approaches infinity. Notice we haven't used L'Hopital on any of these, right? Because it doesn't work. You end up with the same thing. So the e to the x, we have same base here. This is going to be e to the x to the power 1 minus 1/2, right? Because this is e to the x to the first, this is e to the x to the 1/2. 1 minus 1/2 is 1/2. So this is limit as x approaches infinity of e to the x over 2. Okay? Now, even though this is going to grow slowly, this is eventually going to go to infinity, which means that e to the x grows faster. Faster than e to the x over 2. Interesting, right? As this goes to infinity, this is going to go to infinity. Awesome. So, now, a couple reminders that are going to be helpful for your homework. The derivative of log base 2 of x, and the easiest way to think about this is just to use your log rules. This is natural log of x, when the base goes in the basement, natural log of 2. And then 1 over natural log of 2 is a constant, so I can pull it out. Times d dx, natural log of x. Derivative of natural log of x is 1 over x, that is 1 over x ln 2. You might remember in general, log base a of x, the derivative of it, is always 1 over x times natural log of a, not natural log of x, natural log of the base, right? So, this guy, you can do the same thing, right? We could do this as 1 over x squared times natural log of 10, right? So hiding 10 right there, and then chain rule by multiplying by 2x. Then one of those x's will cancel, you can do that. Or you can pull that 2 to the front, so 2 times derivative, right, because of log rules, of log of x. So that would give you 2 times 1 over x ln 10, which gives you the same thing, right? The 2 comes to the top, the x cancels on the bottom, you end up with the same thing either way. So this guy right here is going to be used for some homework problems. So a little summary here. If you want to compare f of x to g of x, just take the limit as x approaches infinity, f of x over g of x. You might have to do some creative limits, some creative algebra maybe, but if it ends up being infinity, then f of x is faster. If it gives you a number, then they're the same. And if it gives you 0, then f of x is slow. Okay? And all those examples we did just to kind of show that you have lots of different techniques you might have to use for evaluating limits. So now I want to end with a little bit of continued thinking. We're going to use this a lot more in Chapter 9, but this idea of x factorial, it's going to come up a ton in Chapter 9. And it's interesting to kind of compare a linear, a polynomial, x to the n to the power, exponential, so like a to the x power, and x factorial, right? A natural log x we know is kind of on the bottom of the barrel. So this is kind of the order that they grow faster. And it's an interesting proof to show that x factorial grows faster than a to the x. And that's true for any a. Any a. So no matter if a is e, or 5, or 7 billion, it doesn't matter. X factorial actually will grow faster. And if you want to talk to me more about this, it's kind of cool. We'll try to prove it a little bit better in Chapter 9. But it's an interesting proof, and it's worth thinking about. So if you want to try to write out a little proof for this, it kind of just takes some logic and some thinking about what factorial means. Be happy to discuss through that with you, because it's a pretty cool thing to talk about. So I believe that's it. Hopefully this wasn't too distracting with the airport noises behind me. I love you guys. That's why I'm here. Have a great day.